Okay, so welcome to today's lecture in deep learning and neural networks. Can you hear me? Or microphone is on? Yes. Okay. So we started on last Thursday with looking into foundation models and large language models, and mainly like looking at the architecture, at the scale, and so on. So this is like some of the first important step when building some of these large language models. However, we stopped a bit in the middle because we mainly did this first step of training, and then they already perform quite good. However, we'll see that, yeah, you're not there with what is currently done in state-of-the-art models, but there is typically one additional training step, which is called the instruction following or similar names, or reinforcement learning from human feedback. We'll cover some of the topics. So the idea is that we can make these language models better at performing the tasks they're really trained on. While it's, of course, super interesting that they are able to have the zero-shot capabilities, they still have often a bit unintended behavior. We want to look at that, why it might happen, and then see some techniques of doing that. We'll mainly focus on 3 different techniques. The first is the supervised fine-tuning, which is typically always done. Then there is the reinforcement learning from human feedback, which is typically a second step. And this step is sometimes also replaced what is called as direct preference optimization. So we'll look at these 3 techniques and have a look how it works and how we can train our language models to then be even better. So when we're looking at large language models, they have several very interesting properties. I mean, one definitely super exciting thing is that they are no longer there to only perform one special task. They're not only to recognize whether this is a cat or a dog and classify them, but you can have a wide variety of classes solved by the models. And we've seen that, that can be text only, multimodal, and often even this type of zero shot where we can, by prompting the model, try to do that. Therefore, they are by now a very helpful tool to assist the user in several ways. So you all have used this type of chat interaction, and it allows us to by now often communicate in somehow natural language with an AI system. So one example is also this coding example. So I guess you all have seen that you can do something like natural language to code, so that you can automatically generate some type of code and use it. So it seems to be a very nice and intuitive way of having ability to communicate with an AI. And especially we have a more general solution that we don't need dedicated models for each, but we have one solution which can be several. However, there is some type of misalignment. So if we're doing the traditional training, in our training, the objective is to do the next word prediction. We see that this is a quite simple task. However, we hopefully have discussed that there is a lot of knowledge needed for that. It's one of the most successful applications of self-supervised learning. And so it's a very nice training objective because we can train in a self-supervised learning method. We don't need dedicated training data, but we can just train on all the text or multimodal content we have. However, this is, of course, something different than how we later really apply the model. So if we apply the model, we are mostly interested in somehow assisting the user. So you should give reasonable answers to prompts, questions that the user has. And there might be a mismatch. So it might be some continuation, which is the next word prediction, is the most probable one, but it's not really what the user is intended for. To give you 2 examples, that can be, for example, if you train your model on all the code in the internet, which is also all there, so you're interested in using it for coding. That means, of course, there is a lot of codes with errors also in the internet. I mean, there's like a lot of people ask, like, this is the code, why does it not work, and things like that. So a lot of data it has seen will be not correct code, but will be code with some type of errors. And of course, the model should be maybe aware of these types of errors in order to help users with it. So it's reasonable to train on this type of data with errors in there. But if you ask him, please generate the bubble sort or generate some sorting algorithm, it should generate the correct one and not give you an example with the typical errors that happen in training data. So you maybe not want to have the most common answer, which might be a wrong one in this case, but you want to have the answer which is correct. So the challenge is that, yes, for some continuation, the continuation is not the correct one, but because you have more often maybe seen the typical errors, you would have also produced the errors. And that is definitely not what we want to have. Therefore, yeah, we'll also call these alignment what we want to do. So we want to align the answers with what the user is expecting. Another example is here, when you have like the prompt, explain the moon landing to a 6-year-old child in a few sentences. What you want to have is, of course, that it does this explanation. However, if you think about where this comes, maybe there's very often, there is this list of questions. So a very probable continuation could also be explain the theory of gravity to a 6-year-old and explain the theory of relativity to a 6-year-old in a few sentences. So what it does, it's not really creating the summary, but it's creating a list of possible questions, which might be occurring even more often in the internet. And so this is a valid answer from a point of view of next word prediction, so of predicting the next word. Creating this list is, of course, a valid thing. But for a user perspective, if you ask the user to explain it and it just generates a list of possible other questions, this is not a helpful AI tool. So we have this type of unintended behavior where it doesn't really follow the instruction. And that is like where we are, why it's called instruction tuning or instruction following. So the question is, how can we make these models able to follow the instruction in a way as the user was expecting? It's also not only that it's following the instruction. Typically with this type of alignment, you try to achieve also other things. It should maybe not make up any facts. Maybe in the internet, there's a lot of made up things, so it should not make up other facts. You might want that the model is not generating toxic text. It should not generate typically things like how you build a nuclear bomb. Maybe a lot of text is like somehow biased in some way. And you also maybe want the AI not to be as biased. I mean, if you train it on the internet, there's a lot of stupid text in there, and maybe you don't want the AI to act like a stupid person, but more reasonable. So the conclusion is, yeah, and like training doing the next word prediction is a very powerful thing. It understands a lot of things. However, it might not be the final solution when we really want to have a helpful assistant. So the question is, how can we continue that, and how can we adapt it to a specific scenario? So how can we now, if you have a language model, how can you enable it to perform good on the task you're interested in? And based on your knowledge you gathered in the last 15, 16 lectures, what would be your solution? Any suggestion? I think the first technique we already had there, and it's decently good. So you have this problem now that it's just generating these examples before. So how would you, if you're now asked as a developer, solve this problem? What could be one way of doing that? Any suggestion? Yes? Yes, exactly. So fine-tuning might be a very good idea. So we have this idea of pre-training and fine-tuning. So what we can do is we take our foundation model, pre-trained model, and we take our task-specific data, and we're doing then getting the task-specific. So we could collect, of course, it might be difficult in a way that you have to collect all this data. I agree, but there is ways of collecting the data, and then you have a model which hopefully will follow the instruction. If we're looking at at the techniques we had done, I mean, you can do like all supervised fine-tuning, so the whole model. We can do adapters, but first stay with just training the whole model. Do you see also some things that could happen that might not be so good in the end? What could happen if you now take, so you see, oh, my model is not good at answering the question, so you collect a lot of question-answer pairs, and then you fine-tune the model to answer these questions, and then you have your model, which now will answer the question and not generate other questions, as an example. What could happen in this case? Any ideas? It could be some thing that is critical and it might happen in that case. Yes? Any idea? Yeah, you seemed like you're.
You get the data, also knowledge.
Yeah.
From the large data set. Then you can, when you find it, you forget.
Oh, forget. Oh, I didn't get the forget. Thanks. Yes, exactly. That is exactly the point. So we might lose abilities that we had before. I mean, if we only do question answering, we might no longer be able to summarize because we haven't seen that. And I mean, typically the thing happens that if you're fine-tuning on some stuff, you might lose these abilities. Of course, you could maybe like train on only like adapters, so you might not lose it too much, but still, then you're only like forcing the model to be good at question answering, but on the others, it will not lose these abilities. However, there is a very easy trick to do that and maybe do it better. Any ideas? Maybe it's too simple, so too obvious. So the very easy thing is we're not tuning one task, we're just tuning in a lot of different tasks, multitask learning. So you're not only doing question answering, you're doing classification, summarization, some type of natural language understanding. So you just have a whole big set of tasks, and then you're doing supervised fine-tuning on that. The hope is then you get a model from your baseline language model, which we had here. You're going now to a supervised fine-tuned model, which is not only good in understanding inks, but it's also good in following the instructions. And typically then you, of course, in order to do the supervised fine-tuning, you can't just give question-answer pairs, but now you have many tasks. You also have to add somehow tell the model which task it should perform. But in large language model, that's very easy. You just give a prompt in a way. So you describe your task as a prompt. So that's a big difference to the models we had before. If you do summarization, typically in an encoder-decoder-based model, you would give the input text in your encoder and generates a summary in the decoder. But you don't have to tell the model that it has to do summarization because it's only made there to do summarization. So it's implicitly in the model. Here we want to train on many tasks. So for each data point, we have to also specify, okay, this is the task itself. And the nice thing is with this large language model and the understanding, we don't have to invent artificial tags to do that, but we can do that in a natural language description. And this type of supervised fine-tuning is then what people refer nowadays as instruction fine-tuning. So the idea is that we have a collection of data sets where we have tasks given as instructions, and then we jointly fine-tune on all these tasks. So it could be that please answer the following question. So we have question answering. We had last time this chain of thought thing. So a chain of thought fine-tuning, answer the following question by reasoning step by step. And we have again the apples, and then you see here, there is the answers, what the language model should suggest. So in normal question answering, it should be the just the answer in step by step. It should do something like that. And of course, now we really want to, I mean, the idea is in instruction fine-tuning that we do this type of generalization to the next level. Before, typically, when we talk about generalization in machine learning and deep learning, it means you should not only be good in solving the examples from the training data, but you typically are interested in the performance on the test data. So if the model is good in classifying some images in cats and dogs, it should not only be good in classifying the images in cats and dogs from the training data, but also on other images on cats and dogs. However, the task is always classifying cats and dogs. Here, now, of course, we still want to have the ability to solve other problems. So if you give other question answering, it should also be able to answer the other types of questions that we haven't seen, or the other questions that we haven't seen. But we also want to have a second type of generalization where the model can even solve tasks which is not seen. So if you have now the question, can Jeffrey Hinton have a conversation with George Washington, give a rational before the answer? It should answer that in a way where maybe this type of question is very different from the previous one. Maybe it should even do summarization. So of course, there is still a level like how much generalization you can do. But in general, you want to have the ability that you're not only generalizing to other examples of the same task, but also to some new tasks. Of course, that is not a hard boundary. I mean, when something is a new task, or whether it's just a different data point of the same task, I mean, there is a lot of open things, and you can say, oh, all of this are somehow dialogue systems where a user asks something, then it's all the same task. So yeah, there is, of course, a bit, variability in that, but generally the idea is really that we are trying to go to very more different examples than we had before. In order to do that, one important thing is that we really scale up the number of examples and so on we have. So for example, there is this supernatural instruction set where the authors collected 76 types of tasks. In total, it was like 1,600 different NLP tasks with expert instructions and so on. So here's like one example where it's about small talk strategy. So given an utterance and the recent dialogue contents, output yes if the utterance contains a small talk strategy, otherwise no. And then you have here even positive or negative examples. So if you do the utterance me too, I hope you have a wonderful camping trip, then this is like a small talk strategy, while my item is food too, that is the output should be no. So you see that there is you're trying really not to train on individual tasks anymore, but scaling things up to very many different tasks in order to do that. Here is an example of the task. So a lot of tasks were about translation. Not surprising, if you want to do translation, you have to do a lot of different languages, so you get a lot of different tasks. But we also have question answering here, and yeah, very different type of task that people train this model on. So the idea is really that we are no longer having like dedicated models for one, but you want to have a model which can solve all the tasks. And I mean, the language model is a very good starting point for that, but it does have the unintended behavior, so you try to improve it in this way. Here are two examples of how it's done. We talked about the T5 model in I think last week already. So that's now a language model which had the encoder-decoder architecture. So it's a bit different to like the GPT style. but you're seeing typically similar results. And what is here? So this is a normalized score on 4 benchmark suits. And the very interesting thing is that, so we have the baseline model here with the score, and then you have the fine-tuned model on that. And here we have the difference. The interesting thing is that this type of supervised fine-tuning even leads to more improvement for strong models. So while if you have the baseline, of course, is already different. You see the strong model is better than the baseline model, but you really see the boost when doing this type of fine-tuning. So you have a very good, strong model, but in order to really like solve these tasks, they just need this bit of doing the right thing. They mainly know it, but they are not aligned in some way to give the correct type of answer. So that you have to do in this type of supervised fine-tuning, and then you can really like benefit from that. So the pre-training is essential, and we really need large models, but to then like really use this power of the large model, we need some type of fine-tuning in the end to get the best performance. Some other, so here is one example, like where it's about like logic. So if you have false or not false or false is, and then think step by step, you see that the baseline Palm model, which even has 400 billion parameters, isn't giving the right answer. But if it then has the Palm output, the FLAN, which means that it was supervised fine-tuned, you see that it gets the right answer. You also see that it somehow changed the format. So this is more the format that it was, I guess, given during supervised fine-tuning, and that it's then using, while here it's maybe more the format that it has seen. Here's also multiple choice, where it gives the right answer C, while here it just like continues giving the text. So it's not really answering the question in doing that. So we get only this type of really following the instruction in a way. Good. Any more open questions for supervised fine-tuning? And this is really essential. So even now as I said at the beginning, we look at like additional techniques, but typically these techniques are then built upon that. So the first step is doing the pre-training, then we're doing the supervised fine-tuning, and then we can do the other steps on top of that. So yeah, what are still the open challenge? Of course, there is like data collection, where, I mean, that's in general, we are not really addressing that, but there's two more things which makes things more difficult. The one thing is there is not a single correct answer. In a lot of natural language text, natural language has this challenge that it's ambiguous, and there is not the one correct answer. So we have these ambiguities. And of course, if we're training in a supervised fashion, we are always telling this is a correct model, and all the other solutions are wrong. Why are we doing this implicitly? How is that encoded during the training, that all the other models are wrong? Any remembering of how we're doing supervised fine-tuning on a language model? So you remember we have the output layer, which has like one dimension for each word. And then we're doing the cross entropy loss, which means we're trying to improve, or we are telling the model it should improve the probability of this one word, which is the correct one. Since it's a softmax layer, if we improve, we can only improve and the sum is 1. So we can only improve this probability if we make all other probabilities lower. So when we're saying this is the correct solution, try that. We force the model to increase this probability and make all the other probabilities lower. So really like enforcing it somewhere, or we're telling it somewhere, this is the only correct solution, and give smaller performance to all the others. Which of course is not really completely correct. It's easier because it's hard to collect like these are the 5 good examples, and normally there is even not a finite number of good examples. So that, of course, is one challenge. I mean, you're a bit getting around with this because you're not training on one example, but on many. And the hope is that, in general, the correct example occur more often, while the really wrong ones never. So you in generally like push more toward that, but of course that's a problem. Furthermore, there's another an additional mismatch is that, training, as I said, with this, you're saying this is the right token and the others are wrong. And all the errors are equally important or like bad or so. While, of course, when you're evaluating, some mistakes are bigger and some are less big. So if you're adding a not in there, that's quite a big mistake because it's changing completely the meaning of your sentence. If you're just phrasing it a bit different, that's normally not a big error. Even if it's maybe not completely wrong, all this isn't really introduced in the supervised training. The only thing is this is correct and all the others are wrong. So you're making this type of hard decision, although it's not that hard in reality. It's not that like there's one correct and all the others are somehow wrong. So we should check, can we do it a bit different? And one idea to do that is, can we directly optimize the human preference? So the idea is maybe we can humans say, this is a good answer, this is a bad answer, this is a medium good answer, and so on. And so can we directly try to optimize that the model outputs an answer which the human like? So can we somehow say, get ratings like how good the human likes the answer, and then we are training the model to give answers that really agree what the human would like to have. That's exactly what is like the ultimate goal at some point. I mean, what you want to have is you have an AI system which is helpful to the user. So therefore, can we directly optimize this helpfulness in a way that we're directly providing answers that are very helpful for the user? So, for example, if you have the summary, what you would like to have is, so there are two summaries. The earthquake hit San Francisco. There was minor property damage, but no injuries. That seems to be, if it's like a news article about an earthquake, that seems to be a quite good rating. It should be. The other one, the Bay Area has good weather, but it's prone to earthquakes and wildfire. It's not wrong. I mean, this claim is somehow correct, but it's not really helpful for the summary about like some earthquake in the Bay Area. So you would get a lower rate. So if we have this type of data, the question is, can we train a model that is really like generating the answer which it thinks gets the best reward? So you're no longer trying to predict the most probable token or something like that. But the aim is, can we do it in a way that we are directly like optimizing this type of reward? So what we somehow want to give is, you're searching for the answer S here, which gives you, according to the model, and where the reward is the biggest. So the idea is our model P has a probability distribution over all the possible answers, and now you want to select the ones where the reward of the model has the largest reward. And there is typically one technique which is very helpful in this type of scenarios, and I guess many of you know that, and that is the idea of reinforcement learning. And we're only covering that very over the top, so only what is really needed here for. There's a whole lecture about reinforcement learning, which will give you more details about that. But we are trying to like a bit get the basic idea that is used to fine-tune or to tune large language models. So typically, it's a thing which has been solved for a long time. A lot of reinforcement learning is, for example, used on robotics or on games, also with deep learning models. And the idea is always we have our agent, our AI model, in our case, our language model, and it observes something from the world, gets some input, and then it should give an action. And based on the action, it gives a reward. And there is the problem is that reinforcement learning for language modeling is very, very challenging. What are the type of actions that a language model could do? Or would you see it? Yes?
Yeah, almost infinite.
Yeah, but what is the action first? That is correct.
And say something.
Yes, exactly. So the answer, the generated text is the action that it can do. And the problem is this space of action is very, very big. I mean, each position, it can do 50,000 words or so typically. And then you have sequence lengths of several, like, so the number of action a language model can do is really, really, really high. And that's, of course, typically a challenge in doing that. So this wasn't too successful for some time, but especially in Instruct GPT then, and what is then also used in Chat GPT as a last step, based on so-called the PPO algorithm, there is a very successful way of doing that. And that's what we want to look a bit into today, how it works and how we can train our language model with a reinforcement learning algorithm to work that way. So the idea is we want to optimize the expected reward of the model. So you want to change the parameter in a way that the expected reward that we get, so the sum of all possible answers with the probability of the answer times the reward, that we want to maximize, so that in average we get a very good reward. The nice thing is, first, we can do that. I mean, if you formulate it this way, that works directly. We can just adapt our neural network learning strategy. So we do gradient descent. So we take our current parameters and then change them based on the derivation of this one. Well, that seems now first to be very similar as we did. So before we had some loss function, which we want to optimize. Now we have this expected reward. So that seems to be the first step good. Does anybody see some type of challenge in there? Yes?
As this year's new way to define a reward for the work figure.
Yes, exactly. That is, I mean, typically we cannot assume that this reward function is smooth and that we can calculate the derivation at all the positions. And we know, hopefully, from the beginning, that's essential to train. Otherwise, we can't do gradient updates. So we have to somehow deal with these non-differentiable functions. And there is this policy gradient methods for reinforcement learning, for example, reinforce. And we'll do like a very brief overview in 2 slides about that, so don't worry. But you should get a basic idea of how you can still train the language model to do that and to do this type of updates using some type of reinforcement learning. So this is most of the formulas in there. We're going step by step, but yeah, it's not too much, I guess. So what we want to do is we have to calculate this gradient. We said we want to update our parameters in the right direction to maximize this type of expectation. So in order to do that, we have to calculate the derivation of this expectation with respect to the parameters. That's exactly as we did with our loss function, so it's just a difference. So what we can do then to calculate that, so the expectation is the sum over all rewards times the probability of this sequence. So the reward for all sequences times the probability of this sequence. First, don't think about that this is a maybe infinite number of it. So, but in general, this can be the expectation value, you know, hopefully from math is always the probability of the event times the reward we get there, because it's the expectation of the reward and that we are doing. Now, if you look at that, the reward is independent of your parameters and only the probability depends on your parameters. So you can move the gradient in there, and then you have the sum of all the reward times the gradient of the probability of this. Now you're doing some what is referred often to as a log derivative trick. So if you have the derivation of a logarithm of something, you can use basic derivation rules. That is 1 divided by the inner thing, so the times the inner derivation. So this one is just the derivation of that. It's independent of what we have seen before. This is just basic derivation. So log x, the derivation of log x is 1 divided by x. If you have now the x something in, you have to do times the inner derivation. So that is just normal calculation of it. Now you have here this general formula where you can just apply like algebra on it. So if you multiply it with the probability, you have here just the derivation of P of S is P of S times the derivation of log P of S. That is just basic MS. And this formula now here, you can use and apply it to our formula we had here. And that is the application here. So we start again with what we had. Then we put in, instead of the derivation of P of S, we put the formula at the end. That we have it here. And now here we again have an expectation value. So it's the expectation of the reward times the derivation of log P of it. So the derivation of the reward of the expectation of expected reward is the expectation of the reward times the derivation of the log probability. This we have, and that's the main idea we have in order to calculate really this type of stuff. So how can we now use it? So of course we can still not. So this is again the derivation we had at the beginning. Now this is a reformulation we had on the last slide. Now, of course, this expectation we cannot directly solve. However, if we can't calculate it exactly, there is a way of estimating it, and the idea is you just do like m random examples according to your probability, and then you can estimate this probability by 1 divided by m, the sum of the value inside. So you have to sample m examples according to the probability distribution and then apply them. That's what is referred to as Monte Carlo sampling. So you randomly sample them, get them, and do it this way. And now you have a possibility to estimate this expectation value, and we can use it. So we can now calculate the update as our previous value plus alpha times 1 divided by m times this value. So this is a way of trying to estimate this gradient. Yes?
How do we define the reward in a nice way if we have so many sentences we can produce?
I mean, the first will come later. So the first reward is really what we're currently looking is we have this human reward. So you don't have like some type of model or something, but you're really collecting things. So it's very expensive, and we're coming to that problem. But assume you sample really examples by your model, then you let users rate them, and that is your reward. So you can directly use the human feedback and optimize your model to really be good as a human. So what it then does, so this was a mathematical explanation. You can also look at more from the practical side. It really reinforces good actions. So if you look at the reward and mainly like look at 2 examples, if the reward is positive, then the thing tries to maximize the probability. So then it tries to maximize this probability. If the reward is negative, it tries now to minimize the probability. So it does that on the log level, but if you minimize the log probability, you're also minimizing the probability, so that is somehow the same. So that is more intuitive. So that is all, of course, a lot of simplification in here, but to give you a basic idea of how that works. So what we are now able to do is, if we really collect human ratings on which of these answers are good, you sample answers, you rate them, you can use this feedback in this way to really optimize your model to give good answers in the way. So what we really have achieved is now we can take our language model, we can pre-train it, and then we can use the model, always let the human rate them and continue training it to get the final model. In order that we now get a model which is not just in generally good, but it's really aligned to what a user wants us to answer. It's using the background knowledge, but then it's optimized in a way that it's giving us the good answer. Any more questions on that? Good. So I guess from this picture, you see things aren't solved yet, because otherwise there wouldn't be so many steps in between. So what is the open problem? And you addressed that already, right? The human in the loop is somehow quite an expensive thing. If you think about that, if you train, you want to train on a lot of examples, you always have to ask the human in between which one is the right one. So that seems to be not a very good idea. What do we know about humans? Yes, they are very good and good feedback, but maybe can we replace them with an AI? So can we somehow, instead of having always a human rate the answer, can we have a model which rates the answer and tells us how good that is? And that is the basic idea here. So we collect this training data of ratings, and then we're not using these ratings directly in the feedback, but we are taking a step in between. We are training a reward model now, which tries to do this mapping, which giving an output tells us how good the rating is, and then we are using that as reward. And the idea is that hopefully, again, can generalize. So we are not only getting reward for the data points we have collected, but we can generalize that to new data points and also use them there. This is now a test. So how would you build such a reward model? Any ideas what type of architecture or model you would use? So you have the answer by the system. Maybe you also have the reference, and maybe the question, and then you have to create a score. Yes?
Must be some kind of regression.
Yes, and what you're talking about the last thing, what would you use as basic model? Yes, you can even do it easier. We have our very strong language model, which is good at predicting stuff and understanding text. So we are just taking our language model and then doing exactly as you said. We're doing some type of regression model at the end so that we can do exactly this type of prediction. So we're using another language model or starting from the same, and we're training it as our reward model so that it tries to predict the human rating. And then we can use these labels. So that is the first step. We collect the training data. The next step is now we are training a reward model on this training data. So we are training it to predict, as you said, in the regression, for example, to predict the reward of the human. And then we can do the third step. Now we can apply the reward model during the reinforcement learning to predict the labels for new inputs, which means we can very fast evaluate new types of inputs different questions and so on. So you can train faster on more data. Before we had to only the data we have collected. Now we can also evaluate other things. Of course, it comes to, as always, with a bit of cost. So what could be the disadvantage? Any idea? Yes?
New data that come really from the outside world. It's a little bit like augmented data, so might be overfitting.
Yeah, no, it might not be correct. It just might be that our reward model is not 100% sure. And of course, it will be good at inputs which are similar to our training data, but the more different it gets, it will be worse. And of course, we are very, on the other hand, it would be interesting to get really rewards for the other data. So if the model now generates very other data, it would be nice to also see how good the model is, but then we cannot trust it. So that is one challenge, but yeah, that is a bit with what we have to live. Yeah. Any question? Okay. However, there's one additional challenge, and that's more in the first part in the collection of the training data. I mean, human in the loop is expensive, but also the human judgments are typically noisy and miscalibrated. So if you get something, a 4.2 magnitude earthquake in San Francisco resulting in a massive damage, what reward do you want to give? I mean, maybe that's medium compared to the other, should it know 4.1, 6.6, 3.2. So giving a real rating for this type of model might be quite challenging because it's not directly clear. Is it now a bit better or so? So it's typically quite hard to give you somehow a good model on what is a good scale here. So like really doing this human rating is in that way challenging that, yeah, humans will disagree on that. If there is always a one person who always gives good grades and you have like a distribution of very high grades, there's a very critical other one which gives typically low things. So this of course makes it hard to train a reward model if there is no clear answer in its very skewed distribution. Can you think of a task which might be related but a bit easier to do that and which might be more aligned between different humans?
Pick two problems and choose which is better.
Yes, exactly. So ranking is typically a lot easier to do. So if you have 3 examples to rank them, which is better or which one is either is normally easier. You can give 2, that's already good, but you can also give more. The nice thing is if you give 3, you're not giving like you have not 2 ratings, but you already have 3 ratings. If you give 4, you can combine all the different ratings and you end up with 6 different ratings. So the nice thing is if you have a longer list of ranking, then you can collect a lot of data points. Of course, you have to be careful. It's very difficult to rank 100 examples. So that doesn't work. So you can do maybe 6, 7 or something like that and rank them in some type of way. So this is nice because, I mean, of course, still maybe not all humans will agree on it, but at least typically they are more agreeing on like which one is preferred over the other. And you don't have to like align it to this arbitrary scale and find the right. So that is very good. However, now we have we have somehow a challenge in the way that we need a model which predicts a rating. That was like how we built our reward model. So we need somehow a model which is able to predict the rating of the model. But now we can't train it anymore because we don't have ratings. The only thing what we have is we have some rankings, and that is, yeah, a bit of not directly possible. So how can we train a rating model when we only have this rankings? There is this Bartley-Terry comparison model which tries to do that, which says if you have a rating in order to get a comparison, is model 1 is better than model 2, or the probability that model 1 is better than model 2 is the expectation, the e to the power of the reward from the one model divided by e to the power of the one model plus e to the power of the other model. So you define the probability that 2 rankings are that there is a ranking based on the reward models. And this is interesting because what can you do now? If you have collected ratings, you can take this collected data as a probability thing, and then you can try to fit your reward model to do exactly this probability. So what you're doing is based on this, you're defining a loss. So you're training a reward model that agrees with this so that you have a high probability if 2 models are ranked higher. This expression can be also formulated by the sigmoid function with the difference between the 2 reward models. So the idea is that we are trying to learn a reward model that exactly the rewards here agree with this probability. And this probability is given by our training data. So let's assume, so to say how we are training it, let's assume we have collected our training data. So we have always an input data and then a winning and a losing label or answer to it. And we assume this is sampled from this probability here, saying that the ranking is higher. And now, if we want to train this type of classifier with a reward, it means we can define a loss function in this way that the expectation of the data should be, again, according to log of what we've seen here before, the sigmoid function. So we have now just a loss function, which we can directly train a binary classifier with a loss function. And that we can train, that gives us a reward model. The nice thing is to train that, we don't need really rewards. We only need the type of rankings between models. So you have rankings and you can train then a reward model with this type of loss function because the data here is not ranked data, but it only says that there's a winning and a losing one. Yes?
Okay, we make sure that our samples are like so different that can be ranked or like that are generated so they are.
I mean, that's of course again a problem always with the data. So you're trying to generate, of course, when you generate your data, you have to generate a bit like different types of data, and then you're the human. I mean, you rank them, and of course, humans are also allowed to rank them as equal. And then you're not using this type of examples.
Yeah, but I imagine like for the same input, obviously you get the same output. So how would you then also?
That's a very good question. Any idea how you can get with a large language model for the same input different outputs? Do you have the answer directly?
Yeah, I mean you can. Yeah, I mean you can alter some of the inputs or like begin the word in the output.
No, there's even I mean, yeah, we did explain. So it's a very good point. So we should clarify that. That's very important because for decoding, we didn't really look in like how to generate output. That is true in detail for language model. So we said, I mean, the easiest thing is like this greedy decoding. So you always take the best, most probable and put that in. But that is not the only one. So what you can also do is second, that is one thing. The typical thing of sampling is you're selecting them based on the probability. So if one word has probability 50%, you're taking it with 50% probability. And this way, you can generate a lot of different answers. And the nice thing is the answers are distributed according to the model probability. So, I mean, of course, you don't want to have random answers. But in this case, it's like models with a high probability also accrue more often and more outputs with a low probability. And that's how you can easily generate then for the same input, a lot of different outputs. And then you can ask the users to rate it. It's also helpful because you think that your model is basically good. I mean, if it's completely off, of course, this wouldn't work because you don't have the good answers. But I mean, our intuition is that the basic model is basically good, but it just has still some problems. And that's why, yeah, it's important then to do here do this sampling and extract them from there. Any more questions? What model we use is, we had that already before, so we can do just like the normal language model. The only difference is at the end, you have the regression hat, which you put in here, and then at the last position, you're not predicting really a word, but you're predicting the reward at that. So the only thing you have to train really is an additional regression hat, which predicts you is the answer, how good is the answer at the end. Good. How good does this work? Here's some examples. So here's the validation accuracy. Here's one human gets a reward of roughly like 0.8. If you do many humans, you get even better. And the nice thing is the more data points you have, you're also getting better. And the bigger your model is, you're also getting better. So here you have 8K ratings. Here you have 16, 32, and 64K. But you see the number of ratings is reasonable. I mean, maybe it's not what you can do in your master thesis. Collecting 8,000 data points might be difficult, but in a bigger experiment, that is somehow possible. Meaning that, yeah, that's very nice. We can easily or like train this type of model to get somehow a decent performance. There is, yeah, one additional step on doing that, and that is, yeah, you don't want to change too much. It's again, we don't want to forget what we had before. So you somehow want that the model somehow not goes completely somewhere else. You only want to do like some minor changes. And that's why when you have your pre-trained model and your reward model, we saw that the reward function is the output of the reward model. But you're doing now also that you're saying, oh, the difference between the probability of your new learned model and the probability of the original should not be too big. So you want not go completely off. You don't want to change everything. You only want to do changes that really help you to improve your reward. But if it's mainly changing the probability, so don't do that. So don't change too much. It's somehow similar to what we had before with like having the activations. You say we had regularization techniques. So this is similar, but on a bit different level. So we don't say that the activation should be the same, but we say the overall probability should be not changed too much. We should change somewhere. We should stay somewhere in the end. So yes, so now what we can do is we have our large language model, we train it, we do the pre-training, then based on that model, we do the reward model, we train the reward model here. And if we then have the reward model trained, we can use the reward model to train our final model in order to get the final model with reinforcement. So 3 steps: pre-training, then train the reward model, and then we can do the fine-tuning. And this is really very helpful. So you have model size and how much things are preferred. So you have the pre-trained only. If you do supervised learning, you're getting a bit better, but you're really getting like a lot better once you're getting the human feedback. And you're seeing you're getting even better than what is if you give them the reference summaries. So this was on summarization. So people even preferred then the summaries which are trained using the human feedback more than the original summaries which are used in fine-tuning. Now we can put all of that together, and that is what people referred to as instruct GPT. So now you do the 3 steps. You see now we have it fully folded. So we take our language model by training, or we train our language model using pre-train on the large data. Then we do supervised fine-tuning on a lot of different tasks to get our supervised fine-tuned model. This supervised fine-tuned model is then trained on labeled data as to be a reward model, and then we are combining our supervised fine-tuned model and the reward model and using reinforcement learning in the last step to get then the final model. We're going through all the steps once in detail, but first question.
If I have this reward model, how am I using reinforcement learning to train my model?
The reinforcement model
As the last step, I mean.
I mean, here you need the reward to update your gradients. So you want to update your gradients, and you need the reward here. And this reward is calculated not by the human, but by the reward model. That's making things a bit clear?
Yeah.
Okay, good. Good. So let's go on this example of Instruct GPT, which was like a paper by OpenAI. So they here introduced this technique of instruction fine-tuning. It's mainly what they claim is also used in ChatGPT. We'll see later. The only difference is here it's more on instruction, while the difference they do in ChatGPT is that they are doing the instruction more in a dialogue style, so in a They're not giving commands, but they're more trying to phrase the prompts more in the dialogues. So the first question is, how do we collect the task data? We said we want to have a lot of different tasks in here. So for the supervised fine-tuning, a prompt from the prompt data set is first sampled in order to do that. And the tasks that are there are 3 different ways of collecting a task. So the first one is that the plain one is that they just ask laborers to come up with arbitrary tasks so that you have really a lot of different tasks, because you really want to have a very different, diverse set of tasks. So this one is to really doing that. The next thing is then field shot, where we use the laborers to come up with instruction and multiple query response pairs for this instruction. So you want to, of course, all come up with different types of instructions and so on. And then they had special use cases where like people were interested in OpenAI, and then they again ask labelers to generate correspondence. You see here that's one of the big advantages. If you have a demo system, you can, and especially an online one, you can observe what people use it for and then generate the specific task. Because it's really not easy to come up with these ideas. Of course, we have this fixed set of well-established tasks, but sometimes people will use very different types of tasks in the real world, and you want to also typically address them. So therefore, they put effort in ways of like creating really helpful tasks in that way. And then this is the number of tasks. So they have use cases for like brainstorming, list 5 ideas how to regain enthusiasm for my career, general generation, rewriting, and so on. And here you see the different types of use cases. So there is like generation, open question answering, brainstorming, chat, rewrite, summarization, classification, closed question answering, and so on. And this is then what they got. So they had especially labelers, which created most of the data, and some of the data is also created by the use of the system. So then we have first the input. You see already creating the input is a decent amount of work. You want to have good data with very, very different types of questions. Based on this input, then we don't use the LLM to solve the task, but now we need again people to labelers to generate the output, how it should be. So here, some people went to the moon. So if you explain the moon landing to a 6-year-old, they have to write an explanation with it. So again, we need to create this data, and you see that this can be quite, expensive in a way, creating this data. So write a short poem about a wise frog. You see that the basic is just like an explanation, so that is not helpful, but what you really want to have is that it's then, no, that's not an explanation, it's like other examples again, that's GPT-3, but if it's instruct GPT, it's really giving you an example. Or also, here we have again this thing with explain. And then we have the last step, we then use the data we have there, and it's trained to train this type of model. Done that for several times. Here is 16 epochs, but however, this data, of course, is really, really small to the data GPT was originally trained on. So this is relatively like small type of data. But this is then the type of self-supervised learning. So we see big issues is here to what data to use on and to train it on. Once you have the data, you can do just general supervised learning, as we've done, using fine-tuning on the model to then get a good performance on this one. So this is the first step. Any questions to this one? Yes?
How much gigabytes of data would you estimate that it's fine-tuned on?
I think it's not too much. So, I mean, these are the number of prompts. So they have 12,000 prompts. Of course, they might have several answers for them and so on. but it's not super much data in the way. That's somehow maybe the good thing. If you have a very strong basic model, you don't need too much data for that.
Okay, and this is directly after the pre-training.
This is after the pre-training. Good. Then we have the next step is, as we see here, we need to train our reward model. So the first thing is we have to again prompt our model from the fine-tuned model. So now we're starting with a fine-tuned model, and we prompt the model to give 4 different answers, for example, again. And here again, we see a different type of data. So it's less from the labeler and more from the customer. It's like around, for training, around 32K examples. And so you prompt them, and then you get labels for all these. No, you get 4 of some different outputs for all of them. And there you exactly, as explained, you can, for example, do sampling in order to generate a diverse set of possible answers that are there. And of course, here it's good that you have a decent, good model. If your baseline model is weak, then all these outputs are bad, and that's not very helpful. So you really need a decent, good model to do this type of prediction. Then it somehow makes sense, and you can do this prediction. Then the labeler, now the human work comes, and the labeler has to rank them. Maybe says D is better than C, and that's better than A, and A is as good as B, or something like that. And then we have the last step is that the data is used to train our reward model. So this is now the last step as we had before, so that we're training we use this data to train our reward model in the thing we have seen before. So although we have ranking, we can use that now to train a reward model to give a score for each one using the previous mentioned method. And that is the training of our reward model. Any more questions? Good. Then we can go for the last step. Now we have our self-supervised fine-tuned model. We have our reward model. So we can do now our reinforcement learning and improve our model on the performance of the original model. How are we doing that? We use the reinforcement learning from the step 1 and the self-supervised. So we use the policy network to generate an output. Then we use our reward function to reward it, and use this again to rank them. So one problem is thereby what I mentioned before. If you're not trained for a long time, your outputs might get very different. And of course, another thing is that we can reward all these models. So that is good. Otherwise, when we train, we'll get here different outputs. So we always would have to ask humans, which would make the training very, very slow. But yeah, this is in some way bad, because then our reward model will also not be as good anymore. It's trained to like the input of your standard model and not too good at the other. Therefore, it's important to have this penalty term that we're not changing the model too much, but we're keeping it similar to what we had before. We have seen that before, you know, we had this similar, like the quotient between the original probability and the other one should not be too different. The other problem is that when we are now only adapting to the to this reinforcement objective, we typically see that the performance on some standard or a lot of standard tasks does degrade. So it gets a lot worse on that. And so there's an additional auxiliary task, which is that it still should be good on the original language model prediction task. So we don't want to lose this ability to know which words belong together and so on. So we see that we are extending it a bit. So we have here the objective is we want to minimize the reward, and then we have here the loss that it shouldn't be too different. But then we have an additional loss based on the pre-training, which is the next word prediction task. So you want that the model is still good on the next word prediction task. So you're still keeping that also to be good and doing good performance. And this is what is people refer to as Instruct GPT. And this is also the main idea behind ChatGPT. The main difference is that now it's the type of instructions are a bit different. So they are mainly providing instructions as in conversations and instructions data, and the human is used for both for the user and the AI agent. And then you can use this type of dialogue data set together with the instruction GPT data set, which was transformed into more like the dialogue form. So instead of write a poem for a 6-year-old, you maybe write, oh, can you help me? Can you write a poem for a 6-year-old? So you can easily do it rule-based. So main idea is still the same thing, which is what is currently still used in the ChatGPT based model. Good. Any more questions to this type of training? Good. Then we want to do one last step, and you look at a different type of using this data. So this preference data seems to be very good. I mean, it's very helpful to know what the user prefers or not, because that we're really interested in. And the problem is that using it in the way we're currently doing is typically a quite difficult training pipeline, and it's not easy to sit all these things out. So if we're doing reinforcement learning from human feedback as before, what we're doing is we are taking our preference data. So if you look at it from this data point of view now, then you're using it to train a reward model. That's a normal maximum likelihood training we have. We're just training a loss function using this data to optimize our weights. And then we're using this reward model to improve our LM, our language model, which was from which is like the policy. So what actions to take if you see it more in a reinforcement learning scenario. And of course, so you have only an implicit connection between your data and the LM policy, and setting up this training is a bit difficult. So the question is, can we also directly use this preference data? So can we somehow directly use this data to train our final language model in a way that, yeah, we are training to maximize the language model probability that it really agrees with the preference data. And that is what people refer to as direct preference optimization, or DPO. And that is, the last thing we want to look at today. In order to do that, what they suggested is that you can do a mapping from the reward function to the policy. So which means you can do a mapping from what is a good reward function to what is a good model, what is a good probability. So, and thereby, by doing this analytically, we can, instead of, as in reinforcement learning, where we optimize the reward function, we can use this DPO, we can use this data with preference to directly optimize our policy, which means in policy, in this case, is our language model. So we can directly optimize our language model by having a mapping between the reward function and the optimal model. We can directly do that and use. And we want to both look at the math and how it's then trained to see that. So what did we have? So this is again the maximization we had before. So our reward model, we want to optimize it in a way that we are maximizing the expected reward of our model, and also it's not too far from the reference or the initial policy. So we have a reward function R here, and then we have two policies or language models, the ones that we're training and the ones that we are referencing. And the ones we're training is on the one end here. It shouldn't be too different from the original one. And other one here is used to generate your answer. So the expectation value is here. We take input from our data and we sample our output based on the language model. The language model generates it. And then the expected reward by the model should be as big as possible. The nice thing is that we can analytically find an optimal solution for that. In the DPO paper, there's an exact derivation of that. But here we can just have a look at that. So basically it says the optimal solution is here. So the probability of an output given the input should be some normalization. Then the probability of your initial model times e to the power of 1 divided by beta, the reward of x and y. And then this should be normalized here by all possible answers, the probability of the reward model times e to the power of 1. So the probability of your final model on the one end should, of course, depend on the probability of your initial model, because it should be similar to it. You don't want to go too far from it. But then you want that models with like outputs with a big reward, they get like a higher probability, or like the probability gets increased. And if it's a negative one reward, you see with the expert, your probability should be decreased. So by saying this, you say an optimal solution is this to this thing is that we are getting a policy exactly like that. And that is now, we'll see coming somehow. The idea is, can we directly optimize this one to directly get somehow this solution without going via the reward model? The problem is we can't do that easily because this set is still intractable. We can't sum over all possible outputs. However, we can reformulate things a bit. So we can take our reformulation here we had based on the reward function. And you can solve this one now with respect to the reward function, saying the reward function should then be beta log the probability of your model divided by the probability of the ref model plus some log set here. And now this one we can use in our pairwise comparison data. So we have to keep this definition of the reward model, and then we're getting directly what we need to optimize. So we said that if we have ranking data, the probability of one rank better than the other should be according to this. This was our initial ranking. We take this and put in here the reward function based on the definition here. We can just insert this definition, and then we're getting here the definition of our. So this is how the probability should be defined based on our model. So we can use that one now as our loss function. So we want to train our model in a way that we minimize or we maximize the expectation, so minimize the negative explanation. Now we have here, based on the data that we collected, so X, Y, Y, W, and YL, so the winning label and the losing label, we can now optimize our model P theta in a way that it fits to this data and maximize the expectation of this function. So you can now directly train your model with the data that we have collected. So the big difference is we are no longer training a reward model like a reward model on the preference data, but we are directly optimizing our final model based on that data by minimizing this type of loss here or maximizing the expectation. Yes?
So then it's not reinforcement learning anymore, right?
Yes. So this is as here. So we're doing reinforcement learning in the second time. Here we're doing directly maximum likelihood training. So we're maximizing the likelihood of the training data. But the important thing by doing the steps, our training data is not the correct answer. So that is here the difficult thing. So the training data is not, you don't want to maximize the correct answer, but you want to maximize this rating. So that is the most helpful. And that you can do with all these tricks here. And that, of course, has the advantage you don't have to do any sampling anymore. You can directly optimize the data that you have and also get decent results and make use of this type of preference data that we have there. Yes?
How can you again, like directly, rate, make the rating of the model better, or like how do you formulate the task again?
I mean, this is the loss, so that you want to minimize this type of loss from your reference model, and this is now the expectation value on this training data. So you have the training data, and then this is your loss function that what you want to use, which is based on the probability of your model and based on the probability of the reference model, so the initial one. And you see you want to increase the probability of the winning one, and you want to decrease the one of the losing one. That is mainly the idea again. So if you have this example, you want to increase the relative probability of the winning one, but you want to decrease the one of the losing. So here you have the relative probability difference between your initial model and the reference model. For the winning model, you want to increase the probability. For the winning one, you want to decrease that.
It's the same model, right?
This is the same one, yes. P is the model. So these two are the model that you're changing, and the lower one is your reference model in our case. That is the initial model after supervised fine-tuning, which you don't want to change too much. So that should stay hopefully the same, and you want only to do minimal changes. Any more questions to that? Yes.
The end of the model, do you put some type of other head on it? Is there regression head or classification head or anything?
No, because we're not training here any reward function anymore. Here you're just training to maximize the probability of the output.
So it's just again a word generation.
This is just a word generation test. Good. So in total, we had today a bit more math. I hope it was still understandable. What you should keep in mind is, on the one hand, the instruction tuning, that it's important that the model doesn't just do what is most probable, but follows what the user wants. We do the reinforcement learning from human feedback, and we did the direct preference optimization as two different techniques of how to do that. Any more questions? Good. Then we have on Thursday the practicum, where it's also about foundation models.